Alright, so hopefully this is recording. I'll double check before I upload, but really quickly, I guess this is just my approach to the fact that lots of folks were out on Friday. Figure we can make a video of the notes, and then folks who already took the quiz have the opportunity to watch the video and take notes. Those who are going to take the quiz today can watch this video and take notes later. And then everybody can watch it as many times as they feel they need to. So really quickly, the do now warm-up, it is related to what we'll be talking about, and essentially we're just combining like terms when it comes to the radicals, but in certain instances we will need to reduce the radicals before we determine whether or not we have like terms to combine. Square roots, which will be familiar, but then also fourth roots and cubed roots, etc. So let's get into it, right? The warm-up. I know it's not terribly common, but I like to read this as, 7 times x plus 3 times x minus 4 times x. And that repetition of sound, right, the times x, times x, times x, that's what's going to tell us that we have like terms, is sort of my opinion on the subject. So 7 times x plus 3 times x, because they're both times x, we know that's going to be 10x, or 10 times x. Again, it's not customary really to say times x, but maybe we should. And I think that point will be clearer when we start talking about radicals. But anyway, long story short, you know that 7 times x plus 3 times x is 10x, or 10 times x, and then minus another 4x, or 4 times x. They're all like terms. Anyway, combining your like terms, 5 times x, 2 times x, that's 7 times x. I wish you would stop doing that. 7 times x, and then I guess that's it, minus 7 times y minus z. Anyway, these, because we are saying, right, 3 times the square root of 5 plus 7 times the square root of 5, that's why they're like terms, and we'll have 3 plus 7 is 10 times the square root of 5. Alright, I could tell you generally when it comes to radicals, right, we have the same index number and radicand, same index number and radicand, and maybe that's what makes them like terms, and we'll just do 3 plus 7 is 10. Or like I said, the repetition of sound, right? 3 times the square root of 5 plus 7 times the square root of 5 is why we can add those coefficients. Anyway, here, right, 2 times the square root of 11 minus maybe 1 times the square root of 11. So initially that is just the square root of 11, right? 2 minus 1, square root of 11. But here, the square root of 44, you got to do a little bit of work. And all right, if you're with me on the prime factorization bit, right, I would argue maybe it's 4 times 11, and then 4 is 2 times 2. 11 doesn't break down, it's prime, right? And I said the index number is a 2, so you're looking for pairs, right? If we put those back together, this is the square root of 4, which is 2. I don't know. So you could do this a couple different ways. I know there's a bunch, and you probably already have your own. But anyway, 3 times the square root of 11 plus this ends up being 3 times 2 times the square root of 11, or the square root of 11 plus 6 times the square root of 11. Don't forget there's a coefficient of 1 here. So all told, 1 plus 6 is 7 times the square root of 11. If you just write 7 times the square root of 11 like that, without the multiplication symbol, that's fine. Alright, that's kind of the gist of it. Just trying to get the same index number and radicand. That's how you know you have like terms. And obviously working to familiarize yourself with reducing square roots, cubed roots, right? Writing them in simplest radical form, right? I mean, our square roots, I hope it's this simple, right? And then the square root of 75, that's the square root of 25, maybe the square root of 3, maybe the square root of y. I don't know, I just keep breaking stuff down. Oh, keyboard. 5 times 2, let's just put those things back together. 6 times 5, let's put those things back together. Oh, look at that, right? 10 times the square root of 3y plus 30 times the square root of 3y. Alright, you can either say, once again, same index numbers and radicands, or 10 times the square root of 3y plus 30 times the square root of 3y. Again, that repetition of sound. 10 plus 30 is 40 times the square root of 3y. Alright, D. Can't be simplified. Alright, square root of 5 isn't going to break down at all. Square root of 10, sure, maybe that's a square root of 2 times the square root of 5. Does not simplify. So that's it. You don't have the repetition of sound, right? 9 times the square root of 5 minus 4 times the square root of 10. And you can also say, well, the radicands are different. So index numbers, sure, are the same, but the radicands are different. Not like terms. Can't combine. All right. What's going on with higher indices, right? Higher or greater index numbers. 4th root of 32. If you're not familiar with the fact that, right, I mean, I can show you a couple different ways, right? So the 4th root of 32, that's the 4th root of 16 times the 4th root of 2, and the 4th root of 16 is 2. Right, I can simplify this 4th root of 32 that way. Oh, this will be interesting. Using a different computer and stylus than I typically do, so anyway. Right, or I'm going to take that 32 and say it's 2 times 16. Oh man. 16, 2 times 8. 8, 2 times 4. Alright, if you need to do this, what I said was like your index number is 4, so now you're looking for groups of 4. I want to make sure we put that back together basically, and make sure that you are looking at this 16 at some point, you know, so that you do begin to recognize that we're essentially talking about the same thing, right? Different way of showing the work to get to the same point. The 4th root of 16 is 2. Alright, I don't want to just say that, well, it's the 4th root of, you know, we can do that, 2 to the 4th times the 4th root of 2, and then people say, oh, well, these just cancel, it becomes a 2. Anyway, I mean, right, or I'd said, maybe if you're talking about radicals, you could say, well, there's a group of 4, and we just get rid of them, and a single one goes out front, and whatever's not circled goes underneath, right? I mean, I don't want to say that exactly, right? I want to make sure that we're either looking at this 16, so we're recognizing this perfect, you know, the 4th degree of something, right? 2 to the 4th power is 16, you know, or at least looking at it this way. That group of 4 represents this 2 raised to the 4th power. Anyway. Right, so then what am I looking at? The 4th root of 162. To try to cut to the chase, right? I mean, I know this is 81 times 2. I know that the 4th root of 81 is 3. If you don't, then I hope we can break down that 81 to 3 times 27, then 3 times 9, then, right, the 9 and everything, so forth. So, right, 3 to the 4th times 2 is your prime factorization, but, right, it's the 4th root of that times the 4th root of that. Yikes. So, 3 times the 4th root of 2. I understand how to break down the 4th root of 32 and the 4th root of 162. So now you can say, well, that's negative 2. The 4th root of 32 becomes times 2 times the 4th root of 2 minus 7. The 4th root of 362 becomes 3 times the 4th root of 2. Negative 2 times 2, negative 4 times the 4th root of 2, negative 7 times 3, minus 21 times the 4th root of 2, negative 4 minus 21, negative 25 times the 4th root of 2. Alright, getting a little lengthy here because just trying to break down those radicals. I will try to go faster here. Breaking this down, my x's, I know I can do x cubed, and I'll have 1 left over. I know I can do counting by 3's, 3, 6, maybe a single y left over. I don't know, that's a shorthand way of doing it, I suppose. 64, I do know that that is 4 to the 3rd power. Okay. And now the cubed root of x cubed is x, the cubed root of y to the 6th is y squared. This is times the cubed root of xy minus, this is 4 times the cubed root of xy. We do have to combine these, right? They are both cubed root of xy terms, cubed root of xy terms. Or again, xy squared times the cubed root of xy minus 4 times the cubed root of xy. We're going to find a way to either, we can either talk about this as factoring out that cubed root of xy, and we can write it like this. Okay, or I guess I would just say, well, they have like terms. I do have to subtract their coefficients. The coefficient, first coefficient, as xy squared, and the second coefficient is that negative 4. I have to, you know, right? I'm doing that subtraction, but that's my coefficient, and that's the sort of term, right? They're like terms. They're cubed root of xy terms. So one way or the other, either factoring or forcing that subtraction between these odd coefficients. Anyway, moving on, right? Cubed roots here, right? I got 6. Cubed roots, I know that I've got 16. 8 goes into 16, that is a perfect cube. And then counting by 3 is z to the 3rd to z to the 6th. Whoops, z to the 6th. And then cubed root of what's left would be a 2 and a z. Alright, we can go over this stuff as much as we need with breaking down the cube roots and square roots. Hopefully I typed this one correctly. Square roots 100, and then counting by 2's, z to the 2nd, z to the 4th. I'm going to have left over a 2, right? 100 times 2, and then z to the 4th times z. So this will become z times 2 z to the 2nd times the cube root of 2z. This will be 4 times 10 times z to the 2nd times the square root of 2z. And I think that's it. I think I'm just cleaning up my coefficients because these are not like terms. Despite the radicands both being 2z, both being 2z, they have different index numbers. This is a cubed root, this is a square root. They're not like terms, right? Or again, repetition, when you read this, 12z squared times the cubed root of 2z, cubed root of 2z, plus 40z squared times the square root of 2z, right? They're not like terms. We're not going to go any further than that. So just cleaned up those radicals, basically. Radicals with fractions. Not sure how long this recording's going, but last 2 examples here. All right, perform the okay, so I think normally I could try to reduce this, but because this is a perfect square, I think I'm going to leave it alone. Let's see, 4. Yeah, it wouldn't be too helpful. So anyway, I have to figure out why my computer keeps doing that. Square root 32, square root of 36, right? 2. Let's see, I can divide each of these by 9. This should give me a 3. This would give me, what, 12? I don't know how great that'll be. Anyway, let's just stick with the same thing here. Alright, so I got 2. Square root of 32, I hope, is the square root of 16 times the square root of 2. Square root of 36 is 6. Square root of 27, hopefully a square root of 9 times square root of 3. 108, what is that? Is that 36 times 3? Yeah, see, or I guess if I had divided by 3, you're going to get to the same spot. Anyway, I do hope that we see that the square root of 3 will reduce with the square root of 3. Alright, I hope we see that. So then this becomes 2 times, right? I got 4 square root of 2 over 6. Oh man, that's going to reduce, isn't it? And then 2 times, this will be a 3 over 6, which I guess reduces 2. So, I know multiplying fractions, trying to figure out the best way to explain and show the work. But right, this is going to be a 2 times 4 square root 2 over 6. You know what? I don't have you guys arguing with me over the best way to show this stuff, so I'm going to do it. I'm going to do it my way, man. I'm going to do some prime factorization, right? I'm going to say this 4 I can break down. So I love doing this stuff and trying to really show people how, fractions work. 6 is 2 times 3. I like the prime factorization rather than just slashing things out. But anyway, at this point, yes, I will, I guess, slash some things out. Let's maybe change some colors and just say, like, this factor of 2 reduces from the numerator with this factor of 2 from the denominator. And that's it. That's all I can do with that first fraction. Here, of course I messed up. 6 is 2 times 3. I thought I switched to the eraser. This 6 is 2 times 3. Silly. So now the 2 reduces with the 2. The 3 reduces with the 3. What's left? That's all 1. Alright, folks. So then we end up with 4 square root of 2 over 3 plus 1. Do we have to combine those? Do we have to get a common denominator and say, yeah, who knows, man. Alright, so then 4 square root of 2 plus 3 all over 3. Or, oh my goodness, I don't really care. Yeah, I don't really care. Wondering. Anyway, some form of these would be fine. Whether if you left it here, I'd be okay, right? If you left it here, I'd be okay. I want to say technically, yeah, I don't really. Sometimes we'll tell you like a plus or minus bi when we start talking about complex numbers. Anyway, it's neither here nor there, but they're all equivalent. Talk about it. Square root of 80 over the square root of y to the 4th. The square root of 81 over the square root of y to the 10th, right? 80, I would hope you recognize it's the square root of 16 times the square root of 5. Otherwise, you're going back to prime factorization, making factor trees to get a bunch of 2's and a 5, right? And then sure, I guess I can say that's y squared or something like that. Plus, square root of 81, I think we know is 9. The square root of y to the 10th, just since I'm writing it like this, why not? So 4 times the square root of 5 over y squared. Plus, sure, 9 over, what is this going to be, y to the 5th? Do they want us to try to, that would be, it's kind of annoying, but to get a common denominator, I need to multiply by y cubed. So do I have to do this? I don't know. Why we would do that to you. Anyway, maybe I would make it 4y cubed times the square root of 5 plus 9 all over y to the 5th. Something to that effect. Or do we have to put the real before the, or sorry, not the real, the rational before the irrational? I don't know. Those are different answers I can come up with, but again, we can talk about, what's acceptable and what your final answer needs to look like. But that's the gist of it, right? So I went back to square roots, which is weird, but understanding the fractions, using that rule, whether it's a square root of a over b or a cubed root or a fourth root, whatever, just take the respective, root of the numerator over that root of the denominator, using that sort of, I guess, nth root of a over b, nth root of a, nth root over b. Alright, so again, some people might still be taking the quiz. You'll work on some of these problems. I'll get to work on creating an answer key. And those of you who are watching this sort of, I guess, Monday night, try to get some of these problems done. But that's about it. Thanks for watching, guys.